Welcome to our walkthrough of LeetCode problem number 38, Count and Say. In this problem, we'll explore a fascinating sequence generation technique where each term is derived by counting and saying the previous term. Let's dive in and break this down step by step. The count and say problem is an interesting challenge that asks us to generate a sequence of strings based on specific rules. The task is to compute the nth term of this sequence. Let's start by understanding how the sequence is structured. The first term is always the string 1. From there, each subsequent term is generated by describing the previous term as a count of consecutive digits, followed by the digit itself. For example, the first term is 1. When we describe it, we say 1 1, which gives us the second term, 11. Then, describing 11 as 2 1s, we get 21 as the third term. Following this pattern, 21 foot becomes 1211, because it's read as 1 2, then 1 1. Finally, 1211 turns into 111,221, described as 1 1, 1 2, then 2 1s. Your goal is to implement a function that can generate the nth term based on these rules. Now, let's discuss the input and output format for the problem. The input is an integer, n, where n represents the position of the term in the count and say sequence that we need to compute. The value of n is constrained between 1 and 30, inclusive. The output is the nth term in the sequence, represented as a string. For example, if n equals 1, the output will be 1, since the first term in the sequence is always 1. This simple example highlights the base case in the sequence. The function must be able to handle inputs within the specified range efficiently. To understand the sequence further, let's look at another example. Suppose n equals 4. The output here should be 1211. Let's break this down to see why. The first term is 1. Describing it as 1 1, we get the second term, 11. Next, 11 is described as 2 1s, giving us the third term, 21. Finally, 21 foot is described as 1 2, then 1 1, resulting in the fourth term, 1211. This step-by-step construction follows the rules of the sequence, where we count groups of consecutive digits and describe them accordingly. Continuing the pattern, let's analyze another example. If n equals 5, the output should be 111,221. Here's why: starting from the first term, 1, we describe it as 1 1 to get 11. Then, 11 becomes 21, described as 2 1s. Next, 21 foot is described as 1 2, then 1 1, resulting into 1211. Finally, 1211 is described as 1 1, 1 2, then 2 1s, giving us 111,221. This example shows how the sequence evolves and highlights the importance of accurately counting and describing consecutive groups of digits. It's also important to consider special cases when solving this problem. The smallest input, n equals 1, is straightforward because the output is always 1. At the other extreme, the largest input, n equals 30, requires handling larger terms in the sequence efficiently. Additionally, the function should correctly manage transitions between terms with single-digit groups, like 21 foot, and terms with multi-digit groups, like 111,221. By ensuring that the function can handle these intermediate cases accurately, you can create a robust solution that generates any term within the given range. To solve the count and say problem, the goal is to generate the nth term of a sequence based on a specific pattern. Each term is derived from the previous one by counting groups of consecutive identical digits and describing them. One straightforward approach to tackle this is the brute force method, which involves iterative string manipulation. We start with the base case, where the first term of the sequence is simply 1. Then, for each subsequent term, we examine the previous term, count how many consecutive digits are the same, and construct the next term by appending the count followed by the digit. This process is repeated until we reach the desired term. The advantage of this approach is its simplicity. It directly mirrors the problem's description, making it intuitive and easy to debug. However, as the terms grow longer with each iteration, the repeated string concatenations and the increasing size of terms can make this method inefficient for large values of n. The time complexity is roughly O and *m, where m represents the average length of the terms. While this approach is simple to implement, it comes with a trade-off in performance when scaling to higher terms. Now, to improve upon the brute force method, we can use an optimized approach involving a two-pointer strategy. Instead of processing the string in a naive manner, we use two pointers or indices to identify the start and end of each group of identical digits in the previous term. By counting the length of each group and building the next term incrementally, we reduce redundant operations like repeated concatenations and unnecessary retraversals of the string. This makes the process more efficient while still adhering to the same overall complexity of O and *m. The two-pointer strategy reduces intermediate overhead, offering better performance in practice. However, it does come with its own challenges, as careful handling of indices is required to ensure correctness. Additionally, we could explore a recursive approach, where we define a base case for the first term and recursively compute each subsequent term from the previous one. While recursion aligns well with the sequential nature of the problem, it introduces extra space overhead due to the call stack, with a complexity of O and *m in time and O, n in space. This makes recursion less suitable for larger values of n, as it risks stack overflow. Both these alternatives, two-pointer and recursion, offer unique advantages but also introduce additional complexity or limitations compared to the brute force method. Given these options, the iterative brute force approach emerges as the most practical choice for this problem. While it is not the most optimized, it is straightforward to implement and sufficient for the typical constraints of the problem, such as n being less than or equal to 30. The two-pointer strategy, though faster, adds complexity to the implementation, and recursion is avoided due to its space inefficiency and the risk of stack overflow for large inputs. One key observation that simplifies the iterative approach is recognizing the self-similar structure of the sequence. Each term depends only on the previous one. This means there is no need to store all the intermediate terms, just the current and previous terms are sufficient. To optimize string concatenation further, we can use a list to build the next term and join it into a string at the end, which is more efficient than repeatedly appending to strings. While the brute force method may be slower for large inputs, it strikes a balance between simplicity and efficiency for the given problem constraints, making it the preferred strategy. To understand the count and say problem, let's start with the sequence itself. The sequence begins with 1, and each term is generated by describing the previous term in terms of consecutive repeating digits. For example, starting with 1, the next term describes it as 1 1, which becomes 11. The process then continues iteratively. The algorithm to solve this problem starts with an initialization step where we set the first term as a string, current equals 1. If the input n is 1, we immediately return this term since it's the base case. Otherwise, the solution involves iteratively constructing each term up to the nth term. During each iteration, we prepare to build the next term by initializing an empty string, next_term, and a counter, count, to track consecutive digits. We then traverse the current term, comparing each digit with the next. If they match, we increment the counter; if not, we append the count and the digit to next_term, which captures the count and say description. This iterative process repeats for n1 iterations to generate the desired nth term. When a group of identical digits ends, either because the next digit is different or we've reached the end of the string, we append the count and the digit to the next_term string. After processing all groups within the current term, we update current to point to the newly constructed next_term. This ensures that each term builds on the previous one. Once we've completed n1 iterations, the string stored in current will represent the nth term of the sequence, and we return it as the result. The key insights here are that each term directly depends on the previous one, and generating each term involves a single traversal of the string, making the process efficient while maintaining clarity. The algorithm's structure, with its step-by-step counting and appending, naturally aligns with the problem's requirements. Additionally, the growth of each term's length is roughly linear with n, impacting the time complexity. Thus, the algorithm processes a total number of characters proportional to the sequence's growth, and its efficiency is a direct result of this iterative design. The data structures used in this algorithm are simple yet effective. Strings are the primary choice for representing both the current and next terms. They allow for straightforward concatenation and traversal, which are key operations in this problem. Additionally, a single integer variable, count, is used to track the number of consecutive identical digits, making the implementation clean and efficient. Now, looking at the complexity analysis, the time complexity depends on the total number of characters processed across all terms up to the nth term. If the length of the ith term is L_I, the total complexity is proportional to the sum of these lengths, O, L_1 plus L_2 plus L_n. Empirical observations show that the length of each term grows approximately linearly with its index, leading to an overall time complexity of O, n squared. The space complexity is determined by the largest term generated during the process, which means it is the O, max_length_of_a_term. These insights highlight the balance between simplicity and efficiency in the algorithm's design. Edge cases are an important part of this algorithm's design. For the smallest input, when n equals 1, the algorithm simply returns 1 without performing any computation, as this is the base case. For large input values, memory usage becomes crucial since the terms grow in length. The algorithm must handle these efficiently to avoid unnecessary overhead. Another edge case involves groups of digits reaching the maximum single-digit count, such as 99,999, which requires careful handling to ensure the count is processed correctly. To solidify these concepts, let's walk through an example where n equals 4. We start with the first term, current equals 1. For the second term, we traverse 1, count 1, and construct next_term equals 11. We then update current to 11. For the third term, we traverse 11, count 2 ones, and construct next_term equals 21. Again, we update current to 21. Finally, for the fourth term, we traverse 21 foot. Here, we count 1 2, followed by 1 1, and construct next_term equals 1211. We then update current to 1211, which is the desired output for n equals 4. This step-by-step process demonstrates how each term is built by counting and describing the groups of digits in the previous term. To optimize the algorithm further, we can use a list to construct next_term instead of directly appending to a string. This reduces the overhead associated with string concatenation. Another optimization involves pre-computing and storing terms for frequently requested n values, which can significantly save computation time for repeated calls. These enhancements ensure the algorithm remains efficient and scalable, even for larger inputs or repeated use. The solution to the count and say problem involves generating the nth term of a sequence where each term is a description of the previous term. The sequence starts with 1, and subsequent terms describe the count of consecutive digits followed by the digit itself. For example, the sequence begins as 1, 11, 21, 12, 11, and so on. The implementation begins by initializing the first term of the sequence as a string 1. The function iterates from 2 to n, generating the sequence iteratively. For each term, a new string next_term is constructed by processing the current term digit by digit. A count variable tracks the number of consecutive identical digits. When a different digit is encountered, the count and the previous digit are appended to next_term. This process ensures that the description of the current term is accurately built. At the end of each iteration, the current term is updated to the newly constructed next_term. The loop continues until the nth term is generated. Finally, the function returns the nth term as the result. This approach is efficient and operates in O, n*m, time complexity, where n is the input number, and m is the average length of the terms in the sequence. This implementation handles edge cases like n equals 1 seamlessly, as the base case is already defined. The function is concise and avoids unnecessary overhead, making it both clear and effective for solving the problem. In this Java implementation, we start by defining a class called solution and a method named countAnSay that takes an integer n as input. The first term of the sequence is initialized to the string 1, which serves as our base case. To generate the sequence iteratively, we use a for loop that runs from 1 to n1. Inside this loop, we use a string builder object named nextTerm to construct the next term of the sequence dynamically. We also initialize a variable count to 1, which tracks the number of consecutive occurrences of a particular digit. Next, we process the characters of the current term 1 by 1 using another loop. If the current character matches the previous one, we increment the count. However, if the characters differ, we append the count followed by the previous digit to next term. After that, we reset the count to 1 for the new digit. This ensures we group and describe consecutive digits correctly as we iterate through the term. Finally, after exiting the inner loop, we append the last group of digits and its count to next term, as the loop ends without appending the final group. We then update the current string to the contents of next term, which becomes the new term for the next iteration of the outer loop. Once all terms up to the nth term are generated, the method returns the final value of current. This implementation constructs the sequence efficiently by iterating through each term and describing its digits in order. With this approach, the problem is solved iteratively, ensuring clarity and correctness in generating each term in the count and say sequence. The count and say problem revolves around generating a sequence where each term describes the count of consecutive digits in the previous term. The sequence starts with 1, and each subsequent term builds on the previous one. For example, the first term is simply 1. The second term, 11, represents 1 from the previous term. For the third term, 21 foot, this means 2 ones based on the second term. The fourth term, 1211, indicates 1 2 and 1 1, and the fifth term, 111,221, represents 1 1, 1 2, and 2 ones. This sequence grows as we describe the counts of digits iteratively. We'll now break this process down step by step for different values of n. When n equals 1, we're at the base case. The first term in the sequence is simply 1. There's no calculation here, by definition, the output is 1. Now, let's look at n equals 4, where we start with 1 and generate terms iteratively. First, for the second term, we process the string 1. There's one occurrence of the digit 1, so we append 11 to form the next term. This updates the current string to 11, marking the end of the first iteration. This iterative process will continue to transform the string as we move towards the fourth term. To generate the third term, we process the current string, 11. Here, we count 2 consecutive occurrences of the digit 1, so we append 21 to the next term. This updates the current string to 21 foot, completing the second iteration. Next, for the fourth term, we process 21 foot. First, there's one occurrence of the digit 2, so we append 12. Then, there's one occurrence of the digit 1, so we append 11. This gives us the next term, 1211, which becomes the new current string. At this point, we have successfully generated the fourth term in the sequence. For n equals 5, we follow the same iterative approach, starting again with 1 as the initial string. The process for generating the second term gives 11, just as before. Similarly, the third term is 21 foot, and the fourth term is 1211. These intermediate steps remain consistent with the process we've already discussed. Now, we're ready to generate the fifth term by applying the same principles to the string 1211. To generate the fifth term, we start with the current string, 1211. First, there's one occurrence of the digit 1, so we append 11. Next, there's one occurrence of the digit 2, so we append 12. Finally, there are 2 consecutive occurrences of the digit 1, so we append 21. Combining these components gives us the next term, 111,221, which is the result for n equals 5. At this stage, we've built the sequence up to the fifth term using the described iterative approach. There are some important observations to note about this problem. First, each term in the sequence is derived by counting consecutive groups of identical digits in the previous term. This involves maintaining a count for each group and appending the count followed by the digit to the next term. The algorithm operates with a time complexity of O, n asterisk m, where n is the number of terms to generate and m is the average length of the terms. Ultimately, the sequence evolves by iteratively grouping and counting digits, and understanding this process is key to solving the problem efficiently. To analyze the time complexity of the count-and-say function, we start by examining how the terms in the sequence are generated and processed. Each term describes the previous term, leading to a sequence like 1, 11, 21, 12, 11, 111,221, and so on. The length of these terms grows approximately by a factor of 1.5 with each iteration. Empirically, the length of the nth term can be approximated as O, 1.5 n. Now, for each term, we iterate through its characters to count consecutive digits and generate the next term. This step requires O, length of the current term, operations. Since the length of the nth term is roughly 1.5 caret n, processing a single term takes 1.5 caret n time. This forms the foundation of our time complexity analysis. When considering the total work done across all terms up to the nth term, we need to sum the processing times for each term. This results in the series 1 plus 1.5 caret 1 plus 1.5 caret 2 plus 1.5 caret n1. This is a geometric series, and its sum is dominated by the largest term, which is 1.5 caret n. Therefore, the total time complexity for generating the nth term is 1.5 caret n. Now, for space complexity, we focus on the storage requirements during each iteration. At any given step, we need to store the current term as a string and construct the next term. The space needed for this is proportional to the length of the current term, which is approximately 1.5 caret n. In addition to the storage for the current and next terms, the algorithm uses a constant amount of auxiliary space, such as counters and indices, which do not depend on n. This means the auxiliary space does not contribute significantly to the overall space complexity. As a result, the final space complexity remains 1.5 caret n. Comparing this approach to a brute force method, a naive solution might involve generating all possible terms up to a maximum length and checking their validity. This would lead to much higher time and space complexity, making it impractical for larger n. In contrast, the iterative approach used here is efficient, as it generates terms directly without redundant calculations. The time and space complexity, although exponential, are optimal for this problem given the inherent growth of the sequence. The time and space complexity for the countansay function remain consistent across the best, average, and worst cases. This is because the process of generating and processing terms iteratively does not vary with the input, it is always dominated by the exponential growth of term lengths. Thus, all cases have the same complexity, 1.5 caret n, for both time and space. Mathematically, the geometric growth of term lengths can be explained by the fact that each digit in the current term maps to 2 or 3 characters in the next term, leading to an average growth rate of approximately 1.5x per iteration. The sum of the geometric series for processing times converges to 1.5 caret n, as the largest term dominates. Similarly, the space complexity is dictated by the length of the largest term, which is 1.5 caret n. In conclusion, while the countansay problem inherently involves exponential growth, the iterative approach minimizes resource usage and avoids redundant computations, making it the most efficient solution within these constraints. When tackling the countansay problem, there are several common mistakes to watch out for. One frequent error is incorrect string parsing. Instead of grouping consecutive identical digits, beginners sometimes iterate over the string character by character, which leads to inaccurate results. To avoid this, consider using a two-pointer approach or a counter to track groups of digits effectively. Another mistake is off-by-one errors, especially when handling the last group of digits in the string. Always ensure your logic includes the final group when the loop ends. Additionally, inefficient string concatenation can slow down your solution. For instance, using plus equals to build strings in Python has n squared complexity. Instead, use a list to collect pieces of the result and join them at the end for optimal performance. Misunderstanding the base case is another pitfall. Remember, the sequence begins with 1 as the first term, and failing to initialize this correctly will throw off all subsequent terms. Lastly, some attempt to hardcode the solution by manually generating terms up to n, rather than using recursion or iteration, which is error-prone and not scalable. Always aim for a systematic, reusable approach. Now, let's focus on what you need to keep in mind for interviews. The first important aspect is recognizing the recursive relationship in the problem. Each term is derived by counting groups of digits in the previous term, so understanding this pattern is key. You should also consider edge cases, such as when n equals 1 or when n is very large. For high values of n, your solution needs to remain efficient and avoid memory or performance bottlenecks. Optimization is another critical area. Be ready to discuss why using lists for string concatenation in Python improves time complexity, and highlight how different approaches impact performance. During interviews, it's essential to clearly explain your thought process. For example, when asked about n equals 4, walk through each step of deriving the sequence explicitly. Finally, explore related problems to strengthen your understanding of similar concepts. For instance, LeetCode 271 focuses on encoding and decoding strings, while LeetCode 443 deals with compressing strings based on consecutive character counts. Problems like LeetCode 67, which involves binary addition, and LeetCode 49, which centers on grouping anagrams, further reinforce skills like string manipulation and pattern recognition. Finally, let's examine alternative approaches and their trade-offs. A recursive approach closely mirrors the problem statement, but it comes with the risk of stack overflow for very large values of n. This is why iterative solutions are generally preferred. They avoid recursion overhead and are easier to optimize. When it comes to string concatenation, choosing the right data structure is crucial. In Java, for instance, using String Builder provides better performance, similar to how lists are used in Python for efficient concatenation. Using the wrong data structure can significantly hurt your solution's efficiency. Moving on to complexity, the time complexity is O(m*n), where m represents the average length of the terms and n is the number of terms. This arises because generating each term involves scanning and grouping characters. The space complexity, on the other hand, is O(m), which accounts for the space required to store the current term being generated. By understanding and balancing these trade-offs, you can choose the most effective approach for solving the problem. That wraps up our walkthrough of the count and say problem. We learned about sequence generation through iterative string processing and tackled the problem step by step. Remember to practice similar problems to build confidence with string manipulation techniques. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!